他没有来啊，他到台湾是画湾区介绍团队，他是派那个陈
Okay. Meeting starts. The president, please ring an opening bell.
Good afternoon, everyone. Meeting start.
Rotarians, please all rise for the four-way test. The four-way test of the things we think, say, or do. First,
is it true?
Second,
There are concern.
third,
Will it look well beneficial?
fourth.
Will it be beneficial to all concerned?
Please be seated. Rotary song, TPPS, would you please lead us to sing?
然后一会儿都下来。
Sorry. Again.
海瑞来请再赛。
R-O-T-A-R-Y, that spells Rotary. R-O-T-A-R-Y is long on land and sea. From north to south, from east to west, he brought his folk who serve the best. R-O-T-A-R-Y, that spells Rotary.
Introduction of visiting Rotarian and the honorable guest, PP Shumi.
Good afternoon. Today we don't have any. Oh yes, we do. Okay. We have Sophia.
Oh, good.
Jennifer. Welcome and energy. Today's speaker. Okay, enjoy.
Thank you, PP Shumi. President's time.
Good afternoon, my fellow Rotarians. We just welcome our newest member, Serena, and this is the photo that me and PP Lu went to visit. And you can see the lady behind Serena is her mother. They have a business of the caring house. So we went to the caring house to visit, and her mother is really talkative and really friendly to us. And hopefully, is talkative not a positive word? No, I'm sorry. Okay. Well, yeah, she showed like a lot of hospitality to us. And I don't see Serena today, but hopefully she will join us soon. Next. And last week, we had a vacational visit at the Yigao Vernal Manufacturing and Energy Company. And I hope all of you enjoy the trip. And it's a little bit pity that we didn't finish the tour. So maybe next time, if you are still interested in this kind of in this factory, we can arrange another visit again. Next. And this week, sadly, the badminton team, only 4 people left, and Catherine, she got another spot in the same badminton hall. But yeah, she came to have picture with our members. And thank for the 4 members team, Sophia, Joy, and PP Air. I will try to back to the team next week. Thank you. And that's my report of this week. Thank you.
Secretary's time. We'll have sports program on May 25th at the Yongbing Hall. All members and spouses are welcome to attend. And please register with Anne if you are interested. The next, after the regular meeting today, May 4 meeting will have all 4 members, please reserve your time to attend. Program. Speaker introduction. PP Lu, would you introduce the speaker?
Hello everyone, it's my great honor to introduce our fellow Rotarian, Rtn Energy, to everyone. He's a 2nd generation Rotarian. His father is a P.B. Gordon of Taichung Zhongqu, member of Rotary Club for over 40 plus years. His brother is Donnie, Rotarian Donnie of Taichung Zhongzhou. His wife is also a Rotarian in the States at Ithaca, Rotary Club of Ithaca. After graduating from chemistry department of Donghai University, he went to the States and obtained his PhD in material science from Carnegie Mellon University. He's also a visiting professor at Cornell University. He's also a member of Electrochemical Society and Sigma C Scientific Research Society, and I believe you have to be engineers to really understand how prominent those associations are. He's a really true genius. He can explain to me the difference between nuclear power plant and nuclear fusion technology in 5 minutes. So I'm looking forward to today's speech. As many of you know, most scientists or engineers, they're very good with their left brain. And most artists have better right brain development. And Rtn Energy is one of those geniuses who have both very good development in both right brain and left brain. According to himself, back in the old days, he wants to be a musician more than a scientist. 换句话说，就是他是个被材料科学耽误的音乐家。Let's have a big round of welcome for our Rtn Energy.
Thank you so much. Oh, not that mic. This microphone? Has it only
Alrighty. Thank you so much, Lou. Thank you for the introduction. Good afternoon, ladies and gentlemen. My name is Jimmy Chang, and my Rotarian name is Energy. And thank you so much for the introduction. So it's my pleasure to give an introduction of my work, and I hope my presentation won't be too boring. So I hope this presentation is more interactive. So if you do have any questions, please don't hesitate, just raise your hand. Is that okay? Very good. So let's start. Okay, so I'll start with a short showcasing of the energy storage system, and then I will go to the slightly more academic stuff, but or theoretical stuff for materials, battery cells, battery modules, and battery systems. And I'm still thinking how much can I elaborate owing to the constraints of time, but I try to make it clear and easily understood by people. And finally, I've talked about the future challenges. Okay, so, oh, I'm sorry. So on the right, this is my brother, Donnie Chang. He's currently the CEO of Chang's Ascending, and I'm the CTO of Chang's Ascending since 1997. So the company was founded back in 1997. A very short history of myself. The company was started because of my very first patents in my life when I was a grad student at Carnegie Mellon University back in 1997. And it's a materials patent. And that materials is actually the layer structure materials. It's actually the materials that's used by Tesla for the EV. And that material has some problems, intrinsic problems. That's the stability of the structure of the material. I'll talk more about that later. And that's one reason why electric vehicle catches fire, sometimes catch fire. So, okay, so, and then the company was IPO back in 2013 after how many years? 16 years of hard working, let's say. Okay, so started in 1997, in 2005, we have a big change of the materials that's being fabricated. So we call it LFPO, it's lithium iron phosphorus oxide. This material is intrinsically, the structure is different intrinsically from the layer structure materials as I just mentioned. That's the materials being used by Tesla. And then since then, it's a safer materials because the material itself is more stable. And then initially we think this material should be very popular in the market. And then we try to utilize that materials and make it into battery cells and try to provide to many manufacturers like for different applications like terrain vehicle, electric, motorcycle, even lawnmower, etc. But the successful rate is not close to zero, it's exactly zero. Because nobody knows how to use it correctly because of the battery management system is different. And that is caused by the intrinsic difference, caused by the materials intrinsic difference. The Plato, etc., everything is different. So the BMS, the so-called BMS, battery management system, has to be different. So it took us a very long time to get to some applications being mature. For example, like this golf cart. Right now we have more than 500 of them running daily in golf courses by leasing kind of a business model. And back in 2010 and around 2010, when I was still teaching at Mechanical Aerospace, Department of Mechanical Aerospace Engineering, MAE at Cornell. So I had a team with my colleague. We had a team of 150 people, 150 students. I'll show you some videos about that. And then in 2011, we won the first prize of this hybrid vehicle. And of course, the battery being used is the batteries that I provided, my company, our company provided. And then in 2019, it's another big breakthrough. After 5 years hard working, eventually we had our large-scale energy storage systems for UPS, uninterrupted power supply system, being manufactured for TSMC. So now we are the major supplier of large-scale batteries or TSMC for UPS applications. And how big is it? It's 825 kVA. It's about 700 kilowatt. Do you get the feeling? So how big is it? It's about 1,000 horsepower output, the system. Okay, 750 kilowatt is about 1,000 horsepower, because 1 horsepower is 0.75 kilowatt. Okay, get the feeling?
Trying.
Okay, raise your hand. Clear enough? Okay, so this is a very important patent. Was filed back in 2006. That's the materials I was talking about. It's iron-based material. I'll show you a little bit more about the atomic structure of the difference of all different kinds of materials. But this iron material is the safest materials for lithium-ion batteries. In fact, Tesla just announced several months ago they have switched their EV to this lithium iron phosphate. They call it phosphate batteries. That's LFP. And we call it lithium iron phosphorus oxide. There was a story. The major breakthrough of this material is that we synthesize this material in air atmosphere, not inert atmosphere. So the, well, it's a little bit of reverse engineering, how to mass produce this material in normal atmosphere. And then you have to change the structure, and you have to change the electrical conductivity of the material, etc. So at that time, I tried to dissolve some so-called alliovalent cations into the structure that enhance the electrical conductivity of the material. And that enables the materials being successfully synthesized under air atmosphere. That means it can be mass-produced. So once the materials is available, then you can talk about applications, right? Otherwise, there is no way for the market being popular or the applications being popular. So a very brief introduction of very recently allowed patents. The very first patent I got was, I think, started with number 5. So that's 5 million something. And now it's already 10 million. That's the number for US patents. So you can imagine in 10, 15 years, it's exponentially growth of the number of patents in the past 20 years. So very recent patents is state of charge. State of charge, easily speaking, is how many percent of capacity left in your battery, right? So this iron material, we call it the charge and discharge plate, is so flat, you can't use voltage engaging how much capacity is left. So you have to use integration, methods of integrations in doing this kind of a state of charge. So that's the state of charge pattern. State of health is how much capacity is left after so many years of operation. So that's also for life protection. And then high voltage batteries, battery modules system, this is, we call it omni battery modules, because these battery modules can be hooked up to any charging power or charging voltage. And that's still, that makes the system safe actually. And then health monitoring and safety protection, etc. And this page lists about the chemistry, progress in chemistry. So direct deposition of graphene on substrate materials, the graphene treated raw materials, etc. Chemical synthesis. This patent synthesizes lithium manganese phosphate around 120 degrees Celsius, low temperature synthesis. So this that is a breakthrough actually. And then making an electrode free from polymer binder. I'll mention about more about that in later view graphs. Normally, we make the electrode using polymer binders and make a slurry and do the casting on the substrate. And then do the drying, calendering, and then the rolling to make it a jelly roll or stacking. And normally we use polymer binders, but in this pattern we show how to avoid using polymer binders. That means we use drying methods in preparing the electrode. And then the very last one shown here is the characterization of this lithium, nickel, manganese, cobalt, phosphorus oxide. This is high capacity materials. It's much higher capacity. It's about double the capacity of this iron-based material. So that's the next generation materials. Okay, talk a little bit of the business of the company. So we produce new materials ourselves, send them to China, and then we provide all the designs, all the details for them to do the OEMs for us in making the battery cells. And they send the battery cells back to Taiwan, make them into battery modules, and try to put them in series and parallel to make a battery system. Sounds very easy, right? Okay, so various applications. So everyone looks very simple. So this is for street lighting, electric golf cart I just mentioned, and this is for ignition, for cranking, okay, for vehicle starting, and then for EVs, forklifts, and for generator jump up, and then for telecom applications, and the large scale applications like I just mentioned. That's the for UPS applications, large scale for TSMC, etc. And for the grid, that's the container size solutions. Okay, so showcase a little bit of, we call it UPC, and it's actually more like home use system. So it's actually the grid power, the photovoltaics, inverter, and with the battery backup. So let me give a small cartoon for all of you. So on top, that's the inverter. And the bottom is the battery. 3 kilowatt and 3 kilowatt hour battery. You can place it anywhere in your living room or any place that is available. One hand hooks up to the grid. The other hand hooks up to the photovoltaic. So here's the inverter, here's the battery, and the photovoltaic grid, and hooks up to all appliances. And 2 mechanisms for operation. So when grid power is available, the red implies the energy that's coming from the grid. Green is for the green energy. So during the morning, the power comes in from the photovoltaics and charge up the battery. Then it's disconnected. The grid power is disconnected. The whole home will be operated by the green energy. See, you have a reservoir, right? And you have an input, and you're using it. So during the evening, then it comes back to grid power supply until next morning, and then it charges up again. So it's operated like once a day. So every day you charge it up, your power stops, and then discharges. And using photovoltaics energy as the first priority, then it goes back out. When it's done, it goes back out. So that means you can avoid the peak consumptions from the grid, or the grid actually. So when grid power is not available, then it's actually a reservoir. Okay, so during the daytime you charge it up, and then during the nighttime you discharge it all. You can set it to just 110 or 0. Next day, when it comes back to like 50%, you can set. Then it's normal for operation, and it's good for next day. And this application is actually very good for emergency. Considering if there is an earthquake or typhoon, if there is no grid power at all, if you have the PV only, still you can't dry your appliances. But if you have a reservoir with the photovoltaics, no grid is fine. You can use the renewable energy as a power source. Whenever there is PV input, you can use it. And that is very important, especially during the earthquake. So back in 2011, I believe there was a, that was back in 2011, the earthquake in Japan, the 311 earthquake. So during that time, they found out they have a lot of PVs, but they have no power for normal use. So that was pretty tragic at that time. But so that drives the invention of utilization of battery backup systems. Okay, and like what I just mentioned, it's good. This is a typical energy consumption in Taiwan. So during the day, there are 3 peaks. And during the night, there is a valley. So the peak and valley is about 30%. It's actually pretty drastic. So if we can have battery systems like the UTC I just mentioned, you can actually chop them. And then actually, so do we need more power plants? Probably no. Do we absolutely need nuclear power plants? Probably no. And this is a little bit of the address of this EPC issue. So localize the power generation, stabilize the grid voltage, reduction of the load or of the central power plant, and prevention of blackout and reduction of carbon dioxide. So you can imagine if millions of them are installed in every house, and that can mitigate the our grid. So probably we do not need more power plants. And hopefully, I think that's the trend, and it's ongoing. It's ongoing. It takes time. Okay, so a little bit of showcasing of the vehicle that I was just talking about when I was at Cornell back in 2011, 10 and 11. So actually, the duration was like 2 or 3 years, and I worked with my colleagues and my students, or 150 of them, and start the vehicle from scratch. So this is a small TV interview we had at that time. So this vehicle was actually a Honda Civic. The center part is Honda Civic. The front and back, the rear parts are Subaru Simbar. Well, my colleagues, they retired. So started from scratch. So all the weldings, everything are done by students. And these 2 students of mine, one is at Tesla, one is working for SpaceX.
Are working non-stop to get the car ready. We're designing to win, and we definitely hope to play very well.
They're very smart students. They started the vehicle from scratch. So, and this is a motorcycle. The motor that we were using, it's a permanent magnet. Permanent magnet motor. Weighs about 40 kilograms. This is Jimmy Chang, and I think my brother, right? So he's 10 years younger than me. I was talking about because of the breakthrough of materials.
Because of the breakthrough of materials, we can bring down price the batteries to start.
That means it can be mass produced. Very small, but this is a permanent magnet. More expensive.
Advisors say after the competition, they will share their design with anyone who wants to work towards sustainable transportation. In Ithaca, Tamara Lindstrom, News 10 Now. But you don't have to wait.
Okay. So eventually the vehicle, we won the first prize, was 127 miles per gallon equivalent. Acceleration was 6.5. It actually accelerates even faster than Lexus. My student's car, okay, this is a test drive. So you can see behind this car, there was one Lexus, which could not even catch up. Cannot catch the speed of our hybrid car. Okay, we call it coast down. So give a brake from 60 miles per hour down to 0. Coast down. So all kinds of driving tests. And well, I think it's pretty phenomenal. Worthwhile mentioning. The students can get the license plates on the vehicle back in 2011. So these students are amazing. So we got the first prize back in 2011 in Green Grand Prix, and it's 127 miles per gallon equivalent. In comparisons to Prius was 54 miles per gallon back then. So these are the battery packs, 6 of them on board. So these are still staying in my labs even until now for showcasing purposes. So come back to why Tesla battery catches fire. So, well, it catches fire. There are some intrinsic problems that's originated from the structure of the materials. I'll mention about that later in later sections. But that reminds us when we are building large battery systems, like what I said, 550 volt and 825 kVA. That means about 750 kilowatt. Kind of large systems, safety is no bargain, especially when it is embedded or built in TSMC semiconductor industries. No bargain for safeties. They don't even want any smoke issues, etc. Because they have more than 300 billion NT instruments right above the batteries. So that's a very high barrier. So this is a brief introduction of the battery management system. So we have a dry contact control with patents, and then the battery management systems that monitors for all batteries, individual batteries. And if there are any false alarms, it goes to SCADA, that's the data recording system in TSMC. And it's hierarchical. So we make it hierarchical because normally or conventionally, people use brain in collecting all data, and after analysis, then there are commands to ask the batteries to do kind of activities. But actually, we do not use that kind of design. We make it hierarchical. So the batteries knows how to adjust themselves by themselves. And the central part is just, it's kind of level by level kind of control. And it shows that it's the safest system until now. So that's the difficulty in getting into TSMC, and that keeps our reputation until now. So these are the installation records. So it's been widely used in semiconductor industries. Now we expanded to a little bit larger system. This is for automatic frequency control, or mitigating the property or the quality of the grid. So if the grid, if the energy is too much, then it shows the frequency getting higher. So at that time, you want the battery systems to extract some energy from the grid. And vice versa, if the frequency is a little bit low, you need to input energy back to the grid to make the frequency back to normal. That's 60 hertz. And this is 85.5 megawatts, so it's about 150 megawatt hour battery systems. So 1 megawatt hour is about 20 Tesla vehicle. Okay, so 150, that means it's 20 times 150. So it's about 3,000 vehicles kind of capacity. So when it is large, remember it could be a bomb, right? So safety is no bargain. And this is the basic unit that's been used in integrating the field like this. So each one of them is the container, the 40 feet long container. And it goes to 22.8 kilovolt. So large application. Okay, so for each container, it has a 3.1 extendable to 4.6 megawatt hour. So the capacity is pretty big. So, and like what I said, safety, etc., will be a major issue in creating big systems. So it's about 880 volt maximum, and oscillates between 750 to 880 for mitigating the grid quality. Okay. And this is the, you can imagine, that was the spec for the container, and this is the spec for the rack inside the container. So we will have about 20 of them in the container. So this is typical 300 amp hour capacity battery rack. So 300 amp hour and 800, so it's about 240 kilowatt hour. So it's about a quarter of a megawatt hour. That means it's about 5 electric vehicles for one rack. You get the feeling how big it is? So these are the features. So like what I just showed you, the hierarchical battery management system, and then separated monitoring and control. So normally, like what I said, conventionally, the monitoring and control are combined. So if the monitoring is failed, control can be failed. So we make them separated. Monitor has a little bit of control, and we have separate control systems. So either of them failed, the system's too safe. So that's no bargain. And then digital control, flexible in extending the system capacity, because after years of use, the capacity fades over time. So at that time, you want to extend the capacity a little bit. And then, sounds easy, right? Actually, it's not very easy. A lot of technical issues when we're trying to extend the capacity of a battery. And then the related intellectual properties. These are the related intellectual properties directly related to these applications. The cathode materials, the battery balance system, high voltage systems, the battery modules, the Omni modules. Okay, and then a state of charge monitoring and health monitoring and safety. So our company is very different from other battery companies because our strength is not just manufacturing, although we do manufacture. And we have more than 200 patents, US patents, more than 200 patents. And then we have tier 1 companies like TSMC, that's the prestigious company for right now. And then we still have, we continuously have inventions in solving the energy problems for the world. So I'll talk more about that later. Okay, so that was the part 1, the showcasing. Let me see how much time do I have. I think I have 10 more minutes. So the theoretical part, I try to make it concise. And then I may skip some slides when necessary, okay? So this is the layer structure materials I was talking about. So this is the layer structure for the cathode. In Tesla vehicle, it's called NMC. It's nickel, manganese, cobalt. The very first generation is lithium cobalt oxide. You probably might have heard about lithium cobalt oxide. Actually, that was our very first product in the market. So the yellow represents the transition metal. The green represents the oxygen. The blue is actually lithium. So during charging, the lithium will be extracted out. And you will see the slabs. And these slabs are kept by van der Waals pores. Okay, so just like graphite, and this is anode, so it's actually the graphite. So you probably know how the pencil works, right? So when you get the black handwriting, it's because you are getting those layers out and sticks on the paper. So, and actually, each layer is called graphene. Okay, all right. Okay, so during charging, all the lithiums are taken out from the host structure, and it's inserted into the anode. And vice versa, during discharge, all the lithium goes back to cathode. So the capacity is how much lithium can be stored in the structure. And that's a fixed number. And that's the beauty of this material, and that's the beauty of lithium-ion batteries. For lead-acid batteries, if you put in 100 charge, normally you can get only 70 charges out, back. But for lithium-ion batteries, if you put in 100 charges in, you can get 99.9% charges out. So it's pretty stable. And I think you probably experienced the what I just said, just through the experience using your cell phone. And because the anode and cathode both are layer structures, and lithium ions are cycling back and forth, this is called rocking chair cell, just like a rocking chair. Okay, and the other thing worthwhile addressing of this layer structure material is that when lithiums are out, that is when you charge the battery to higher voltage, at that time, because these slabs are bound by van der Waals force only, if heat is there, the structure will distort and become spinel structure and releases oxygen and heat. And if electrolyte molecules are around, organic, then that means what? It can burn, catches fire. Okay, it's called thermal runaway. Okay, I'm going to skip this one. This is a typical test cell that we actually made in our lab, and we use lithium as the reference electrode. So when we have a lithium reference electrode, we can get the actual exact readings of cathode and anode voltages. And that's the advantage of 3 electrode design test electrode. And since we use lithium as an anode, this cell has to be built in a glove box. And the glove box is filled with argon. So you have a very thick gloves, and you have to do very tiny small works in the glove box. So it took me a long time to I spent a lot of time during my grad student time in preparing such a kind of test electrode and test batteries. Okay, just skip this one. Okay, so my very first patent was to stabilize the layer structure material. Recall, I just mentioned about lithium cobalt oxide, right? Can be replaced by lithium nickel oxide, and it's isostructural, it's layer structure. So you can make some magnesium into the nickel layer, if you recall the slabs I was talking about. And you actually, when you get all lithium out and you get the heat, and you can find at 220, there is a big exothermic peak. That's the energy I was talking about, the heat that's being released. And after adding magnesium to some extent, it flattens out. That means no exothermal peak. That means the material is safe. Let me make it short. Okay. Go directly to lithium iron. So this is three-dimensional structure, host structure. And then lithiums are residing in those channels. And these structures are all interconnected. It's represented by polymids. And so there's no chance for distortion of the materials when lithiums are taken out or inserted back into the host structure, and that stabilizes the material. Okay, the other thing is that this is the typical charge and discharge curve of this iron material. See, it's so flat. No, the plateau, only single plateau, and so flat. And make a little bit comparison of layer structure materials. It's sloping, right? And has several plateaus. And you make a differential, you will see the peaks. You will see the peaks, and that represents different phases, phase changes during cycling. So, for this iron material, because of the three-dimensional network of the structure, there is the plateau is very flat, no phase transition at all. And this is the TGA analysis, very similar to what I just showed for layer structure stabilization by magnesium. For layer structure materials, see the exothermic peak around 220. For lithium iron, it's so flat, there is no exothermic peak at all. So that means when lithiums are all taken out, even if there is a heat source, there is no decomposition of the material. So the battery does not catch fire. The battery does not catch fire. So this is the consequence, right? Okay, a little bit of electrode. I just mentioned a little bit of the materials. It was made into a slurry, do the casting on the substrate. On the cathode is aluminum foil. Okay? And then after calendering and winding, it become a jelly roll. 4860 is the Tesla standard for nowadays electric vehicles. So it's wound like a jelly roll. This is a little bit wacky, right? I'm not going too much into that, but there are a lot of problems with battery cells. One very simple thing is that you see the wrinkles. After cycling, actually the electrode changes dimensions. And if it expands or swells, it can break the substrate or break down the substrate. So you'll see the capacity drop immediately after cycling. Or you'll get some materials that's spilling off from the substrate. So that causes the capacity loss. Okay? And this battery cell, 50 mAh. I think for the Tesla battery, for layer structure materials, the 4680, it's a cylindrical battery. It's about this big. This is probably 10 times bigger than that. And why can this battery cell become so big? Because it's safe. See, for the Tesla battery, if the core is heated, when you measure the surface of the battery cell, when you measure the temperature is high, it's already overheated inside the battery. So it's too late. Too late. So you can't make big cells out of layer structure materials made battery cells. But for iron-based material, you can make it big because there is no thermal runaway problem. You see this distinction? Okay, these are the standard tests for battery modules. Okay, so in battery cells, materials is very important. This is for the battery modules test. It's already 150. Let me go to the abusive overcharging as an example. That is, if the battery is working at 26 volt, or we make it nominal 28, we use 58. That means double of a voltage to charge it. Okay. Normally, for lithium, for the layer structure of batteries, if you overcharge it, it just explodes. But for this battery, if you overcharge it, you see the current drops down. Temperature goes high, but not too high. So it's so safe, right? So that's the proof of safety features. Okay, these are the rate capability. I'll talk a little bit 1C and 11C, but just remember 11C means the current magnitude is 11 times bigger than 1C. And 1C is you discharge the battery in 1 hour. So if it's 50 mAh, that means 1C means 50 amp in discharging. 11C means 550 amp. It's shown here. So for a Tesla battery, if it's 50 kilowatt, 11 times means 550 kilowatt power output. And if you divide it by 0.75, that's about 800 horsepower, right? So this power is so good in, we call it rate capability. So we use it for cranking, and it's much better in comparison to conventional lead-acid batteries. Okay, so rate capability is very important, and actually it's also very important for UPS because instantaneous power is very important. Okay, so the essential elements responsible for the system success. First of all, the materials, right? The materials shouldn't exhibit any decomposition behavior, and no heat should be generated. The battery cells, the balancing system, we call it single wire control, that's a hierarchical control, the isolation of control and monitoring. These are the typical important or essential points need to be taken good care of. And levels of protection starting from the materials level, we just mentioned a little bit about the heat property. Cell level, safety vent, etc. To the module level, we have casing. The rack level, we have MCCB, multi-channel circuit breaker cutoff. And to the system level, that is a charge cutoff system. So the whole system integrated several, see, from materials to system level, 5 layers of protections. If it happens like this, this is the mega pack. That's Tesla's container solution in Australia. It caught fire. That's a serial mistakes or failures. So if one mistake or one failure or 2 of them will not cause a problem, but if it happens like this, it's a serial failure. So in designing the system, we should make sure no chance of this being exhibiting in the system operation during the normal operation. Okay, so what's next? So we have a very good energy storage system. That means we have a very good reservoir, right? And next will be the creation of renewable energies. I think right now the availability of renewable energies are mainly coming from the solar, that's the PV, or the wind turbine, the wind energy, right? And in our lab, we have been working on this vision for a long time. We try to use the silicon as the energy source, and it's the most abundant element on Earth. And we're in the stage of breaking through. And so when this becomes successful, that means Elon Musk's dream his dream to Mars can be viable. Otherwise, right now it's one-way ticket. When you go through space, 90% energy has been consumed. You have only 10% one-way ticket to Mars. You're stay there forever. Does that make sense? That doesn't make sense. But I have a team in Taiwan and US, mainly in either, working on this. So applications like this could be odd. It's pretty odd for right now. Sounds like not very viable, right? Because if it's battery on board and you have no place for generation, there's no way to have a flying vehicle like that. This kind of, you call it ads, or you call it new inventions, whatever. The number of this kind of issues, you can see the frequency you see on the magazines or newspapers, etc., will increase over time. And that requires the creation of energy that I just mentioned about. The other thing is, hello?
No, no battery.
Okay, one more minute. Oh yes, time is up, right? Okay, one more minute. Okay, go through. So utilization of these layer structure materials, we can use it for bio applications. Can you believe that? For sensing. So have you heard about the exosome? Exosome.
Exosome.
In Mandarin it's called 外密体. You probably heard about that. So actually this is a brief introduction of how exosome is created and how can it be detected properly, and how can be used for therapeutic means. And okay, in short, exosome is they call it extracellular vehicle. That's the communications between cells. Okay, so yeah, so if the cancer cells, they can communicate using exosomes and in deceiving the T cells. Okay, so you probably know, you can catch a little bit how exosome works, and using the layer structure materials I just mentioned, and it can be used in separating, or many means in working with the aptamers. Aptamers is just like antibodies used for detection of the surface of the cells, the cell surface, and it can be implemented into the exosome itself too, if it's small enough. Using what? Quantum dot. Graphene quantum dot is about 10 nanometers, 20 nanometers, that kind of size. And this kind of thing can be used as when it is activated. We hope to use this being delivered to cancer cells or around the cancer cells through external means in irradiating and making it rotate, eventually kill cancer cells directly. So that's the hope. It's ongoing. Okay, a little bit of philosophy. So I think this one is more important. Being persistent, perseverance, and perpetuation in hard work. Okay, thank you so much. Oh, any questions? I hope it's interactive. So I keep watching Ming, and Ming is a very good supporter. So I like it. I mean, he has been concentrating. So I'm your personal speaker.
I do have. Don't worry about the catching fire.
No, don't worry. The chance of catching fire is small. And actually, after crashing, if there is any heat source, that can induce that kind of stuff.
Right.
And or at home, or if the battery system is aged, if the communication is not as designed, then there are chances in catching fire. Yeah, so still have a good confidence with Tesla. So don't worry about that. But there is something with intrinsic properties
Right.
of materials. You probably heard about that. Yeah. Okay, any more questions?
I see PV just has a question.
That was about Tesla.
Okay, very good. In fact, when the materials were made, at that time we tested a lot of electric. We even tested a lot of all kinds of applications, including terrain vehicles, including the electric motorcycles. Very good performance because it's so flat in voltage. So when the state of charge is 100 to the state of charge is close to 0, the performance is consistent. But for layer structure material, the performance will drop down with the decay.
What kind of stage is your product in? Is it still a prototype or is already a merchandise?
It's already a commodity.
Oh, really?
Yes.
Oh, that's great.
For sure. Because now we are using it for large scales. We can't compete with Tesla.
You don't have to.
Exactly. Although we know what is going on.
Different market.
Different market, exactly. We're a small company, tiny, very tiny.
But important.
Yeah, yeah. Thank you so much. Thank you for your compliment. Thank you. Yes.
Okay. President Jimmy, I'm ready to give to the speaker.
Oh, okay. Celebration. Okay.
Thank you. Attendance report.